Okay, good morning. We're going to start today's lecture. Before I get into the new subject, I would like to make a correction of what I said the last time. Last time we talked about the stoppage criteria, and we listed actually three. I would like to add one more. This is very important because when we do ensemble EMD, many of the algorithm is based on this criteria. This criteria is very simple. It's limited to, I don't care what I got. I limited to my iteration to a fixed time, like 10 times, 20 times, or whatever. Okay, so this is the simplest criteria. And sometimes, if you fix the number of iterations, like I do a maximum, minimum, I do a mean, and then after that I do a maximum, minimum, and mean. I iterate only a fixed number of times. Okay, whether the result outcome is or is not a intrinsic mode function, I don't care. I just make that a fixed number, and you select the pre-select this fixed number of iteration, and that's very different. This, for example, is pre-select a number, but this number is different. This number is that you count zero crossing and extrema. When they are equal, you start to say, okay, that's one time, that's two times, that's three times. This one does not care. I just do the maximum, minimum, mean, maximum, minimum, mean, 5 times, 10 times, or whatever times that you select. In the particular case that we adopt, actually is this fixed time is 10 times. Okay, so please add this to your stoppage criteria, because later we did use this as a very interesting case, because you will find that as you increase the number of shifting, the amplitude becomes more uniform. So eventually, if you shift infinitely many times, you're going to have only FM signal. The AM is all totally disappeared. Okay. Now, having said that, we will talk about the spline, because people ask about this, and I think maybe we should have a little bit of discussion on this particular method, because it is important for us. So I will use 1 hour to discuss this. And this introduction is an outline, and mostly based on what I find in the web. I do have a couple books, but when you get into books, it's a lot more involved. I don't want to get into so deep. What is spline? I remember, I think most of you probably have never used a spline. When I was in college, when we do the engineering drawing, we have a set of what we call the French curve. Anybody have seen French curve? The French curve is a very, next time I will bring a piece of French curve. It's a very graceful shaped curve that you can fit your data point that you connect with a smooth line. That's called French curve. Each French curve has a fixed shape, so it may not be that useful. So a set of French curve, the one that I bought, has 12 large and small different curves. But then there's another thing called the spline, which is a piece of very flexible wood or plastic or whatever. When I was in school, there was a piece of plastic, and with a metal rod inside, so you can bend whichever shape. So if you have, say, like a number of points, you want to draw a smooth curve through the number of points. So you bend this very thin piece to pass through each point, and then you trace that It's much graceful and much smoother than your free hand. And this this spline is, if you look at the dictionary, you'll find that the definition is just a flexible piece of small wood or plastic or whatever to help you draw a curve. And the original use of that is in shipbuilding. When they build a ship, they want the ship to be some graceful, so you bend the wood into that. And when you draw a curve, you just use this thin piece of wood you bend, and then you draw this curve. That's what the spline is. That's the spline used in practical. But then whatever thing that when mathematicians get a hold of it, they're going to inject some rigor and some analysis into it. So mathematically, spline means a curve fitting mostly using certain piecewise low degree of polynomials. Yeah. And when I first used it, I have a confession to make. 10 years ago when I first developed this, I didn't know that much about spline. Yeah. Spline is relatively new. Yeah. So I thought, well, if I can use a spline, then if I use a higher degree, it will actually be better, because higher degree gives me more flexibility or whatever. Turns out, yeah, the main reason to use low degree is that the polynomial, if you use high degree, it becomes unstable. Yeah. And this unstable is called the Runge phenomenon. Runge phenomenon is very simple. Take an example of this function. This function is 1 over 1 plus 25x squared. It's a smooth function. You can take a derivative and whatever. Now, if we try to interpret the equal space point of xi is defined this way. For I equal to 1, 2, all the way to n plus 1. Okay? If you choose n equals to 1, what happens is equal to n equals to 1, 1 plus 1 is 2, so I equal to 1, 2. Yeah. The n equals to 1, so you have I equals to 1, this is 0, so it's minus 1. Now I equals to 2, so then this becomes 2, then n equals to 1, so this is 2 minus 1 is 2, 2 minus 1 is 2. So you get plus 1, minus 1 plus 1, so you get 2 points. N equal to 1, you have 2 points. N equal to 2, you have 3 points. So in between plus and minus 1, you will have equal space the number of points defined by this formula. Now, of course, you can choose any n. You can choose more n, that means you have more points. And you have more points, that means it has more degree to fit. And then what happens is this. If you use, if I have a data, this is the data. This is the data you plot. This is 0. This is the data you plot. This is a very smooth curve. Depends upon the degree of polynomial you try to fit. And each degree of polynomial, you have to have that number of points. 5 degree have 5 points. 9 degree have 9 points. So you think that if you have a higher degree, I may get a better curve. Surprising. So if you choose n equal to 5, then you will fit a curve like this instead of get smoother. And if you take 9, then it starts to oscillate up and down, up and down. And the higher the degree you select, actually the more oscillation you have. It does not really give you stability. I remember when we first started with 3rd degree, we found a lot of overshooting. We thought, gee, if we use a higher degree, we may eliminate this. Turns out that's totally wrong. Yeah, and later we did find out, but in the beginning of the paper, in the 1998 paper, which was written 1996, that's 12 years ago, in the paper I actually say that, well, maybe we use higher degree, we can get elimination of this overshooting. Turns out, if you use a higher degree, the overshooting is even worse. And in fact, mathematically you can show that if you have this function of x, and if you try to fit with a polynomial Pn, the difference between the function and the polynomial in between x equal to plus and minus 1. And as n approach to infinity, that means I get higher and higher degree, this difference approach to infinity. In other words, the overshooting can be so big that it's totally useless. Yeah. So because of this phenomenon, now whether this phenomenon happens every time, it may not be, but it does happen. And what we call the Murphy's law is that if this is possible, and in most of the time it happens to the most unwanted place. Yeah. So because of this Raj phenomenon, we really don't want to use very high degree of polynomial to fit. What is, oh, this is okay. So because of this, we really don't want to use higher order. Yeah. I say, well, if my curve is really fluctuate up and down, what should I do? And the solution is to use piecewise. You cut the curve into little pieces, and in each piece you try to fit the curve. Yeah. You don't try to use a higher order to fit the whole piece. You cut the curve into little pieces, and each piece you generally use a low degree. A low degree should be preferred. Now, at the beginning of the EMD, we tried, of course, the linear. Immediately you think linear is not very good. Linear straight line, that's not very good. We tried the second order. Second order is not good either. Second order, it's parabola, and that looks very ugly. Many of the curve does not converge. Yeah, so many of the case doesn't converge. So we finally settled down in the natural spline, and it's just by pure luck that it worked very well. Yeah, and are there problems? Yes, there are problems. Later we'll get into that, and we will see what kind of problem we have. But in order to avoid the Runge phenomenon, we generally prefer lower degree of polynomials to do. So definition of spline. The spline is that if we have in the x and y space, we have n plus 1 node or data points, control points. Okay, so from x0 to xn, we have n plus 1 points. Now, a spline is a function of x, and that x0, the first section connects from 0 to x0 to x1. And that function exists only in these closed intervals. Once you go beyond this, it doesn't work anymore. We don't need it. Okay, so we have between 0 and 1, we have a function. Between 1 and 2, we have another function. So this is piecewise. We have one function after another, after another, after another. So if you have n plus 1 points, and you will have n functions. That n function, each one work for one interval. So we'll have n function. And each of this is a polynomial. And once you select that degree of polynomial, you have to stick to it. Like, for example, I selected cubic. Then every one of these should be cubic. It should not be, say, linear, then quadratic, and then cubic, or whatever. It has to be all the same function. Functional form has to be the same. Yeah. And then you try to fit this within each closed intervals. And this interval, say, this closed interval share the endpoints, x1, x1, x2, x2, and xn minus 1. They all butt together and share the same endpoint. Now, so the easiest spline is linear. Linear is very simple. I start from I and from xi to go beyond that. Then I've tried to fit yi to yi plus 1. And that's totally linear. This is the slope, and multiplied by whatever the x running from xi to xi plus 1. Okay, so the spline must be continuous at the endpoint because we share the same endpoint. And even though each spline works for a specific interval, so interval 1, the end of interval 1 is the exact beginning of interval 2. So at the beginning and end, each point, it has to be the same. For example, if we check xi, the value has to be equal to yi. Okay, so you write xi, the I for xi. You put xi here, you find xi minus ik is 0. So xi equal to yi. That's fine. Okay. How about s minus 1? S minus 1, using this I equal to s minus 1, then you can write into this form. And into this form, and xi, x variable is still x. You put x in there, and this cancel. So this 2 and this cancel, you get yi again. So for linear, it's no problem. Yeah. Once you started, you started this formula, and this formula will give you a continuous curve. Continuous curve. Curve is continuous, but it has broken points. The curve, the derivative is not continuous, but the curve is continuous. Okay? And quadratic. So what if I go higher? So you go higher is fine. You go higher degree, then the basic form is ax squared plus bx plus c. Yeah. So when you write it out, the general term will be look like this. Yeah. Again, the coefficients, that unknown coefficients are the z1, z2, which is equivalent to this ABC. Yeah. So again, you try to evaluate this coefficient to fit all the curve, and all the curve still has to be continuous. Yeah. The continuity is that si minus 1 equal to si for all i's. And then if you use this continuity equation, you will find that you can derive, actually, if you use si equal, you force this to be yi, and you force this to be also yi si minus 1, just like we had done previously. And if it's I equal to I, of course, this is 0, I equal to I, that's 0, so yi equal to yi. And if this is I minus 1, this cancel that, and these two can combine, and you simplify it, you get this formula. So this formula is very useful. This means that if you use a quadratic form, and once you give the beginning z 0, and the rest of that will follow. This is recursive formula. Everything is fixed based on your value of your control point. Yeah. So this is quadratic. We tried quadratic, and it works terrible. It will just go too far and doesn't turn fast enough. Yeah. So when I first tried that, I thought, gee, this doesn't work. It's not going to work very well. Yeah. It turns out after we tried cubic, it works fine. And then we go to cubic. Cubic is high, it gives us enough flexibility, but it does not give us the Runge phenomena as bad as we show at the beginning. And basically, this is a cubic function which has 4 unknowns that we have to fit. A, B, C, D, we have to fit. Okay, and the spline passes through all the data points. That is xi. If you put I, it has to be equal to y, yi. Okay, this is the same. The spline has to be continuous. Continuous means this point, j minus 1, the end point equals the beginning of the next curve. And furthermore, here we ask for even fancier restriction. That is, the slope has to be continuous. That means the curve, in fact, in the second order, the slope is already continuous. Here, we need the slope to be continuous and the curvature, the second derivative. The first and second derivative has to be continuous. Yeah, because curvature is defined by second derivative. So you require the second derivative to be continuous, means the curvature, radius curvature is continuous. Yeah. So these are the conditions for cubic spline. Even this condition still does not fit. We still can have various kind of cubic function to fit through a given set of n data, and that's where it comes from. That's where different cubic spline will appear. The cubic spline that we use is a specific cubic spline. It's not just all cubic spline. It's a specific cubic spline. The specific cubic spline is this, that first we have to see that how can we, once we ask for the pass through all the data, we ask for the continuity, we ask for continuity, slope, and curvature, why we still have different cubic spline? The reason is this. For n plus 1 points, then we have we need 4n conditions, right? We fit each point. Each point has a cubic equation. Cubic equation has 4 unknowns. So we have 4n equations. We have 4n unknowns. We have n equations. So each equation has 4 unknowns. I have 4n unknowns. To fit 4n unknowns, then we can see how many conditions we have to solve for this, to define this. First, we say that first, every point, every spline goes through the data point. Every goes through data points, we have how many data points? We have n plus 1 data point. So we have n plus 1 conditions. So that's good. We get n plus 1. And then we need all the interior point has to be continuous. Yeah. The interior points, however, we only have n minus 1 interior points. So that's n minus 1 interior points. All the twice continuous differentiable are all at the interior points. Derivative continuity and second derivative continuity. So that give us 2n minus 2 conditions. You add all this together, what you got is 1n, 2n, 4n, plus 1 minus 1 cancel. So we have 4n minus 2 conditions. But we need 4n conditions. So we're still too short. So this curve, this whole spline is undetermined. We cannot determine. It's underdetermined. Yeah. The underdetermined condition, so that gives us 2 free choice that we can play with. And these 2 choice give us different kind of cubic spline. The first, this all come from these 2 free conditions. For example, a clamped cubic spline. That means at the beginning and the end, or any point, you don't need a point. You don't need even beginning. You just select 2 points. So at that 2 points, I need slope to be at a given value, a specific value, not arbitrary value. So if you do not specify that, the slope will assume whatever value the equation will give you. But if you specifically specify a value, and that means that you add a restriction, a constraint. Yeah, and this is sort of like in practice is that you try to draw a curve, but this curve have to go through certain area. That area you apply a clamp it there, so the rotation is limited. So this is called a clamp cubic spline. The nature cubic, this clamp, you think, well, that's pretty good. We just assign certain point that the slope equal to 0, for example. Yeah. That is very subjective because before you fit it, you really don't know what the curve looks like. You really don't know what the slopes looks like either. Yeah. So the better condition, even for clamp spline, is to fit the condition at the beginning and end. So this K most likely should be xn, should be the end point. So if at the beginning and end we say I want the slope to be 0 or at a specific condition, that's very easy to implement. So that's easy to do. So that's much better than at any other point. So clamp spline typically give you the slope at the beginning and end. Yeah. Then the next is the natural spline. This is the one that we use the most. We actually select. The natural spline says that at the beginning and the end, the second derivative equal to 0. That's the only condition. That means the second derivative is the change of the slope equal to 0. Yeah, the slope can be anything, but the curvature, radius curvature, is infinite. Yeah, so it will go out of the at the end. The last point. The last point. It should be should not have any twist. Yeah, this is the easiest condition that you can you can select. So this is what we call the natural spline. It's so easy to implement and it sounds reasonable. Yeah, because it goes out. This second derivative equal to 0 means that I do not use any force to bend the curve, to let the curve go out freely. Yeah. So the second derivative, if x is position, second derivative, as I said, is acceleration. Second derivative equal to 0 means force is free. I don't apply any force to the curve. So the curve go free. That's nature. Yeah. Once you go out of my region, I apply no control to you, and therefore you're free to go. And because you're free to go, there's no force. Nature. Yeah. Another one is a periodic cubic spline. Then you impose on the condition like the beginning and end equal to 0, or the beginning and end of the slope equal to the same, and beginning and end of the second derivative equal to 0, curvature the same. That doesn't happen that often. Most of the data are not periodical. So this periodical may have special application. I would say that this, of course, is the most reasonable thing that I can think of, and this is also pretty reasonable. I mean, lots of applications. You want to draw a curve, and you have a beginning and end point. The beginning and end point, you apply a clamp together. Typically, this slope is the following the first and the second line, the straight line curve. Straight line curve. The slope is fit in that way. So this natural spline is the one that we use all the time. When we in the class, when we talk about the spline, I typically simplify it as natural spline. Okay. There are other fancier splines that actually a lot of people think that the natural spline is not good enough. They want to use other splines. one of one of the spline that have been used very, very often or mentioned very, very often is Hermite spline. Hermite spline is also cubic, but it has some basis function. This is very different. Basis function are not like a cubic spline. Cubic spline does not have basis function, it has a basis functional. I have a cubic function, and cubic function A, B, C, D are changeable. This one, you say that if I define this set is called the Hermite basis. The Hermite basis is, he come up with this 1 plus 2t times 1 minus t. T times 1 minus t. T cubed, t squared, 3 minus 2. And t squared, t minus 1. You ask me why he come up with this? There are reasons behind it. This 2 has very nice property. H11, when it's 0, it equals to 1. When t equals to 0, it's equal to 1. T equals to 0, it's 1. And this value, when t equals to 0, it equals to 0. But the slope at 0 equals to 1. And this curve, the slope at 1 equals to 1. And the last curve is when t equals to H11. The last curve, the derivative of the last curve equal to 1. So each of this has some specific values. And let me show you this curve, how this curve looks like. The curve looks like this. S11 is this. From 1 all the way coming down to 0. We can see. T equal to 0 equal to 1. T equal to 1, it's 0. Yeah. So this function coming from 1 all the way coming down. And the other function has slope equal to 1 and then eventually come to 0. And this is slope, this slope is 1 here, slope is 1 there. And the other one has 1 equal there. So these are the 4 Hermite polynomials. Yeah. Using these 4, you can actually fit. You can select value at the beginning and end, and slope also at the beginning and end to determine this fit. So the typical given P0 and slope at the beginning and the position and slope at the end. The position and slope at the initial and end point. You can fit the curve through that. And the beginning, because this at the t is equal to 0, it's 1, so you say the position equal to my position. It's 1. And the slope at the beginning, the slope is 1, so the t equal to 0, slope equal to m0. And same thing over there. So if you select the beginning value and end value, the beginning slope and end slope, you can fit this curve through it without any problem, and it's continuous. Yeah. So so for any of the more points, you can do the same thing, and you can even introduce a slope value. You can adjust a little bit of the slope value to make the slope value equals to the slope of the points. Yeah. So Hermite spline can be selected sensibly according to our need. Yeah. There are still different kind of Hermite spline. You can find a final difference spline, and you can have cardinal. They are called. They give you introduce another C, which you can select the C to adjust even the tension of the curve. It's a lot of choice. Yeah. However, the one that used by most of the people is the last one. is called a monotonic spline. What is the monotonic spline? The monotonic spline is designed specifically to make the connection between points, in between 2 points, the curve will have to be monotonic, either increasing or decreasing. Now you think that's a very nice property. If my curve is just keep increasing or keep decreasing, it can never have overshoot, right? So the Hermite spline is introduced as a way to make the overshoot small or eliminate the overshoot. At the beginning of HT, we even try the cardinal spline, and it becomes too involved because here it's a C. Each C, you have to. C cannot be constant. If the C is constant, it doesn't work anymore. So C will have to be a different location. You can adjust the C to make the curve tighter. So if it's an overshoot, I draw the line tighter to make the overshoot small. By that, you have to, at each point, you have to interject a subjective condition. And that's not very good. And we are just impossible to introduce so many different subjective conditions. Even if you use the same tension, like all over the place, and that still is pretty subjective. This monotonic spline, however, means that you can go from the beginning and in between each point it's monotonic. Doesn't mean the whole curve is monotonic. Piecewise monotonic. Yeah, only piecewise monotonic. So, in general, the Hermite cubic spline does not guarantee monoticity even for monotonic data. The monotonic even in between data points. Yeah. It may still have up and down, but in between data points, it's monotonic. That's all you have. The advantage is to eliminate overshoot. The price to pay are this. It's nothing, it's free. So the spline has its requirement. So we no longer have the smoothness of the continuity in curvature. Yeah. The second derivative is no longer continuous. When I come across this, I come from the point of view from a mechanics point of view. The mechanics is that the force, the second derivative is acceleration, which represents the force. And if you say the force is discontinuous, it means that I have to apply force and take force away and so on and so forth. That's a little bit too special, too specific. So I decide this without the continuity of curvature, it's not very good. That's one objection. The second objection is that we have to introduce subjective idea of monotonic values. How do you know in between the 2 points is monotonic? We don't know. We fit a curve through given data points, and asking that this curve is monotonic, it's not. It's just as unreasonable as you have overshoot. Yeah. What do you mean by overshoot? Overshoot is that it may take a little bit farther to turn around, but yeah, make it go a little bit farther to turn around seems to be bad, especially we have a gravity-oriented environment. We see, well, it's go beyond what we have. But you really don't know if you maintain the continuous force and continuous velocity, and that is the way that a particle will move. Yeah. So these are the price that we have to pay. Yeah. So of all this, with all this consideration, at the beginning, we, after test different options, now we did go up to higher order. But you see, I did not discuss any higher order thing. Actually, in our test, we went up to the 7th order. And by the time we go to the 7th order, it doesn't even converge. Yeah. Even the 5th order already started to be not converging. Because once you go to the 5th order, then you have to have more conditions that you introduce. Not only continuity in slope, continuity. You have 5n conditions. So what we did is we interject another condition. Another condition is that at each of our maximum, when you pass through the extrema, the slope has to be equal to 0. That sounds reasonable. For the data, the maximum is slope equal to 0. But the spline should not have 0 slope. If you use that condition, however, see the slope at each maximum equal to 0. When you connect the two, you introduce another inflection point. And that inflection point means another scale. So the more you're shifting, the more scale you have. So you never converge, even to the 5th order. So after we tried, even the Hermite polynomial, Hermite spline seems to be very good, and a lot of people advocate using it. We find that these two shortcomings, and we decide not to use it. And let's see the comparison. We use an example. I just made an arbitrary function. This arbitrary function is generated by a random number series. Okay, and I shift the random number and throw away the first few components, add the last few components, I get this. Yeah, this function, and if I fit, this is my data, and identify all the extremas, all the maximums. Yeah, and this is the mean, and I will go through with a natural spline and Hermite spline. And you can compare, see how they look. And of course, you see the natural spline will go pretty smooth. It will go through this, whatever it goes, just go up and down. This smoothness means that not only slope is, not only curve is continuous, slope is continuous, curvature is also continuous. And the smoothness gives you a feeling that, yeah, if I do not change my force abruptly, yeah, this is really should be the way it goes. It really follows your intuition. But they say, no, I don't want that. I want to impose a monotonic condition in between data points. Yeah, and so I will use Hermite spline. Hermite spline is this. See, this is the overshoot. I totally eliminated the overshoot because I impose monotonicity between this point and that point. So this will decrease monotonically. And at this point, it also decreases monotonically to that point, and decrease monotonically, increase monotonic, decrease monotonic. So the increase and decrease are all monotonic. Yeah. Now you see, over here, you will feel that there's abrupt change. Yeah. The abrupt change over here, you also feel abrupt change. And that means when you have a curve going through that, you have to apply force to pull it back. If you don't apply force to pull it back, your mind will think that it should go continuous and come back down smoothly. This, however, did eliminate the overshoot. But is that a desirable eliminating overshooting? Is that a desirable thing? from some cases like this, you think, yeah, it may be. But however, you have to remember, this represents amplitude. Amplitude means in a times cosine theta, that a. Look at this. This is a very large value. And when I flip it over there, even this is not even big enough. So to code this as an amplitude is pretty arbitrary. Yeah, the amplitude, you have to find the real value. Like the simplest thing is to find the real value and the imaginary value. And the sum should be amplitude. That amplitude, this location, should not be limited by a monotonic function. Yeah. Even though there's some overshoot, and that overshoot may not even be a bad idea. Specific condition, specific case, it's hard to say. But to say that it's all overshoot are bad, it's just arbitrary as having overshoot a lot of times. Okay, so and I will draw your attention to this ugly endpoint. Everybody know that endpoint has this endpoint effect. We haven't get to the endpoint yet, so I will leave the endpoint as it is, and later we'll come back and use this example again to see how we fix the endpoint. Okay, so this endpoint, neglect the endpoint. The endpoint is bad, we know that. But here, all I want to know is that the natural spline and the cubic spline are different. This is the maximum, and this is the minimum. If I connect all the minimum, then I can also have a cubic spline, and I have a Hermite spline. And the cubic spline and Hermite spline, again, are different. You can, if you follow the Hermite spline, you will find that you really make abrupt turns. Yeah, and these abrupt turns, it's much better than straight line, but it's almost like the straight line abruptness. Yeah, so this is the cubic spline that we do cut into the data, we do get out and come in and out. But when I first developed the method, I look at the natural spline. I don't know why, I just like it with all the overshoot and everything. So we decide to have natural spline because it's so simple. It does not have any base functions, and that fit me very well. And if you have this upper and lower envelope, and of course, then you can draw the mean. The mean, the natural mean is this. Cubic spline means this. They are different too. Yeah, and if you look at the mean of maximum minimum difference, obviously they are not the same. Yeah, but even though they're not the same, but they cut through the curve the same number of times. Yeah, and that is important because it still define the scale roughly the same. Yeah. Now you can then see that the difference between mean of maximum minimum envelopes. This is the maximum. The mean of maximum and minimum. This is the difference. Their difference. Their difference is again pretty large. See, our data is only 0.2. The difference between already 0.05. It's a pretty high percentage. Yeah. So by using different spline, we will get different decomposition. No doubt about that. Yeah. But using natural spline and the Hermite spline, the difference is not in the scales. The difference is in the energy level. the energy level will be different. And indeed, if we use that mean to compute the first proto-IMF, the first component, so if you reference to that mean, we extract the first component. The first component looks like this. You compare these two curves. Using natural spline, you get this. Using Hermite spline, you get that. You find that in general, the zero crossings, number of zero crossings, are about the same. Yeah. Now sometimes there may be difference. The difference will mostly come from, for example, like these locations. Like if I have a inflection point, whether the inflection point can or cannot be extracted from the splines. Yeah. If you have maximum minimum, no problem. Yeah, we'll have the same scale. So even though we may use different different spline, I think the result is not that dramatic in terms of scale. Yeah, in terms of energy, it may be a little bit, maybe more different than the scale. And with this comparison, at the very beginning, we decided that since there are so many different splines, we will select the natural spline because it's the simplest and easiest to implement. So that's the spline that we use. But there are other kind of splines. Mathematicians, once start to know the spline, they really get develop that into a different subject. In fact, most of you probably have never used a spline as a tool or use a French curve, because now everybody is using computer. I don't know anybody still have the engineering students. Do you still have engineering drawings? 有没有工程画？工程画是用手画还是用 computer 画？ Using computer or use hand? Computer. Yeah, most computer. So computer, all this already fit in. You enter a bunch of number. The computer will probably give you a spline. Just go through that. You don't have to draw like what we did in that. So there's another spline called the B-spline. I participated in one B-spline study with a group of mathematicians. This group of mathematicians is, when I was in the United States, the chairman of the math department at West Virginia University and the chair professor there they are interested in EMD. So they invite me over there and I give a talk, and then I start working with them. And they look at the cubic spline I use. They don't like it. They say, well, this is totally out of control. Let's write down some equations, okay? And then we can use the equation to get the spline. And this equation, the mathematician prefer B-spline. B-spline is short for base spline. That means you have a basis. Now using the basis, you can define spline. This is almost like a Hermite spline. Hermite has basis. But the Hermite basis, it's just whatever I give the cubic Hermite base, cubic basis. So this B-spline is used extensively in computer-aided design, CAD. Most of the computer design use this method. And the generalization of this is called, we'll touch about that, we'll mention that later. But I should not say, perhaps I should use I found the limited use of this, yeah. We collectively means me and my colleague, yeah. So B-spline. So B-spline to talk about B-spline, we first have to talk about the Bezier curve. The Bezier curve is a base function dependent on parametric curve determined by a set of control points. Yeah, it has the following property: the base function are real, a real function, no imaginary. Okay, the degree of polynomial is 1 less than the control point. Yeah, you cannot have a very, very high polynomial, and you have a depends upon, this should be a space there. Depends on how many control points you use. The first and last point of the curve, and the control point coincide. So the curve does not go through all the control points. However, the beginning and the end, the curve have to go to the control point. Yeah, this is very, very different. Previously, we said that all the points have to go through the control point. Here, we let it go. The control point, yeah, exercises certain control to my curve, but my curve does not pass through all the control points. Only pass through the beginning and end points. This is very, very different from the spline that I'm talking about. Now, if you think that this may not work, it still may work, because you can use both either your maximum, each maximum as control point, and you fit a curve in between that maximum. So you still go through that. The tangent at the beginning and tangent at the end point coincide with the control polynomial. The control polynomial is that if you have n control points, you use straight line to connect all this sequentially, and that form a polygon. And the beginning tangent and end tangent coincide with that. And the whole curve is contained in a convex hull. A convex hull means it's a hollow hull. The curve has to sit inside the control polygons. Yeah, the curve has a variation diminishing property. We'll all come back to talk about variation diminishing property. Means if you have a control point, we'll come back to define that. And the curve is invariant under affine transformation. So you give mathematician always bring up all kinds of properties. And I bet somebody, when they found this, they wrote a paper and proved a theory. Yeah, affine transformation means a linear transformation, ax plus b, that kind of transformation. The linear Bezier point is a linear function, p0 plus t, p0 minus p1. Yeah, linearly changed. This t is the parameter. So that's just a straight line connection between the 2 points. And quadratic means 1 minus t squared times 2t, 1 minus t times t squared t. Yeah, this whole thing is come up by a French engineer. Yeah, it's a very cute idea. And you can see the cubic Bezier curve. It's 1 minus t cubed, 3t, t minus 1 squared, 3t squared, 1 minus t, and t cubed. Do you see any form, general pattern? The general pattern is already appeared here. It's a polynomial expansion of 1 minus t plus t. In fact, for cubic, it looks like this. This is the first one. This is the second one. This is the third one. This is the fourth one. It looks almost like, in some shape, the idea, not the shape, the idea looks somewhat like Hermite function, but except that these functions are all positive. Yeah, there's no negative function. And the general term actually can be given by this simple formula. That's 1 minus t plus t. 1 minus t plus t is what? Is 1. Yeah. It's generated by this 1 minus t plus n. Is n equal to 3, then the first one is 1 minus 1 minus t cubed, then 3ab, 3a squared b, 3ab squared plus b cubed. Yeah. So this polynomial, whoops. How do I get rid of this? Oh, okay. Thank you. Yeah. So, so the general functional term is a combination of 1 minus t to the I minus 1 to the ti times p to the i's point. So you can write up the general Bezier curve without any problem. And this curve has a recursion formula because to the n, once you have n plus 1 is whatever function multiplied by that. So the first term is multiplied, the second term is multiplied by that. So it's very simple. And this is what you will get. If we have a control point, it's from here, 1, 2, 3, 4, P0, P1, P2, P3. If you draw a curve, it will look like that. And this curve does not pass through all the control points except at the beginning and end. The beginning and end points of the curve and the control point coincide. So the beginning is a point on the curve, and it's also a point of the control. And the beginning slope agree with the polynomial, the polygon, the beginning polygon and end polygon. So this will go up at the beginning. The slope agree with this, and the slope agree with that. So in between this, I draw a curve, a smooth curve. That's what Bezier curve is. Yeah. Now, once you get this, you can actually expand it into different kind of curves, and that means you can even give it a weighted function, yeah, to make the curve looks more comply to certain shape and whatever. So this is the kind of variation that you may have. Yeah, the B-spline. A B-spline is a generalization of Bezier curve. Its B-spline is even more general than what we called the Bezier curve that I show you. Yeah, and a B-spline with no internal knots, internal control, is a Bezier curve. Yeah, so when you come to B-spline, in addition to the control point, you can introduce additional points, internal points. You can force the curve to pass through the control internal points. That's the difference. So B-spline is better in a way that in addition to control point, you introduce additional internal points. So this make the spline much more complicated than the natural spline. But the nice thing about that is it has a formula, has a recursion formula, it has all kinds of analytical form, and that somehow appeals to the mathematicians. I even wrote a paper with them using B-spline, and the result they got, I should have that added to this, but that's the second thought anyway. So a B-spline is a generalization of Bezier curve. The B-splines, if you have no internal knots, then it's just a Bezier curve. And this formula is come up with Cox and de Boer. De Boer is the major force in making the spline popular. Yeah, de Boer wrote a book called Spline, a Practical Guide to Spline. It's very mathematical. He's a mathematician. He just recently retired from University of Wisconsin. It's a giant to make the spline popular. A further generation of this B-spline is called NURBS. The nerve is non-uniform rational B-spline. Yeah. And this, it turns out, it becomes a very, very popular tool for machine design. Not machine design, for design any shape like automobile and boat and even whatever product using machine. This is the thing. And in fact, NURBS, nerves, becomes almost a noun. Everybody knows that. And I have a book. If anybody wants to look at it, it's by David Rogers. He's one of the initiator of this. And his book is Introduction to Nerves. It's come out 2001. The book is very interesting. It gives you lots of history of who developed the what. And everything is happening almost in front of our eye. It's not a very ancient thing, because all of this need a computer control. And before you have a computer, you cannot have it. And how old is our computer, controllable computer? It's not only after Second World War. And at the beginning, the computer is so rare, you don't get hold of the computer. Only after the 60s and 70s, then people start to actually use the computer more often. So this nerves becomes very, very popular now in the computer-controlled machinery to cut a very smooth piece that's used by them. And so the B-spline, as I said, the general form of B-spline, you can write it out. This is a binomial expansion of the function. You can write out the functional form. The functional form is very messy, but the mathematician is not afraid of that. If you look at the papers that I wrote with them is covered with this kind of formulas. I don't find it appealing. I find it very cumbersome. But next time I'll give you the reference. If you want to look, you can look up that. Yeah. So so this can be generated by recursion formulas given by this formula, and the curve actually compare. You compare the two, you find that the B-spline now have a lot more control points, constraint. You want to find the n, which is the degree of your fitting. You want to find the control points, which is the one that you use to draw the polygon with. Here are 10 points, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the control points. In addition to that, you have 14 more nodule, the internal control point. Yeah. Once you have the internal control point, that internal control point, however, it's not free to choose. The internal control point, you can only have internal control point. The number of that is m plus p plus 1. You cannot have more. If you have more, you'll have problem. You have overly determined the system. Okay? So you look at this curve. This curve is really nice. You have this control box, and this curve will go through like this. It can turn all kinds of corners, and it's still continuous and very nice. Yeah. And what is convex Hall? This is called a Hall, like 0, 1, 2, 3. This is a Hall. The curve have to lie within this. Yeah. So that 1, 2, 3, 4 is a Hall. The curve has to lie within this. And this is a control Hall. The curve lie within this. And, and so on and so forth. So the curve has a certain preferred formula. If you take away the internal control points, however, the curve becomes that. And this is what we call the Bezier curve. This is B-spline. So B-spline has more internal control than Bezier curve. This both has at the beginning, we have to go use the initial and end points. And the initial slope and end slope are the same. But because of the internal control points is lacking in this, so this curve is much less varied than the B-spline. The B-spline can do a lot more because it adds another set of internal control points. So because of that, at the beginning, I really think using B-spline is very cumbersome. Yeah. The property of B-spline. The B-spline, in general, the lower the degree, the closer the curve follow the control points. Again, you don't want to go to very, very high degree. Yeah. Here, for the same number of control points and knots, but a different degree, the spline result looks very differently. For example, this is degree 7. The degree 7 compared with degree 3. These are the control points. Degree 3 will look much more follow the points, control points better. Follow the control points, the Hall, much better than than degree 7. Degree 5 is so degree 7 and degree 3, 4, 5 are different. These are the property of the B-splines. So you don't want to go very, very high degree of go high degree for the B-spline. And B-spline is a piecewise curve. We must have m equal to n plus p plus 1. Claim the B-spline has passive beginning and end. Yeah. It all has strong convex Hall property. In other words, the control box, the curve actually passes within the box. Variational diminishing properties. Variational diminishing property is this. Let me explain. You have this control box. This control box is very contorted. Yeah. If you draw any line, you will see that I go through control point 1, 2, 3, 4, 5. I cut the control point at 5 different locations. Control box here, 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 and here. Then the diminishing property means that if you cut the control box at the 5 locations, then you cannot cut through the curve more than 5. It has to be equal or less than 5. In other words, you can cut through here. Don't cut through the curve at all. You can cut through here. But once you cut through any curve, you cannot cut through the curve more times than the control box. So the variation, in other words, the turn is diminishing. Yeah. And in fact, you can draw any point. Like at this point, you go through control 1, 2, 3, 4, 5, 6. But how many times you cut through the curve? 1, 2, 3, 4. That's fine. You will never cut through the curve more than the control points. Yeah, that's called the diminishing variation. This is one of the property of B-spline. And the affine invariance. Again, you can translate this control point to any linear translation, it doesn't matter. But the big thing here, I use red to emphasize, is that the B-spline does not pass through the control point. Okay. You say, well, it does not pass through, but you say it does pass through the internal nodule. Yeah. So we can select our point we want to be the internal nodule. But then what is our control point? You have to introduce a bunch of control points. Yeah. So in our application, it becomes difficult for us to use this B-spline. Even in a very simple form, we can still use it. And the nice thing about that is that it has a recursion formula, and it has an analytical form. And once you have recursion formula, you can analytical form, you can manipulate the formulas. Yeah. But that, I think, still does not overpowering or improve upon the better properties that we had in the natural spline. The natural spline is very, very intuitive, very direct. You can see it, you can touch it, you can plot it out. But here, you don't have that other than your complicated algebraic formula. The formula is only complicated algebraically, nothing fancy, because it's still just algebraic formula, polynomial. Yeah. So this is the variation. So this is our summary. The summary is that the difference between different spline seems to be huge. Yeah. You look at some very simple choice of spline. Hermit versus cubic, we already seen. They are so different. So different spline will give us a very different answer, it seems. Yeah. But based on principle of least interference and maximum smoothness, we selected the natural spline for the basis. I selected natural spline for very simple reasons. I want to be smooth. I want that my hands off. I don't want to, every time and now and then, I'll bend the curve myself, because I have no a priori knowledge to bend the curve the way that it fit me. Yeah. Because when we analyze the data has its own dynamics, has its own process, controlling processes. Yeah. And that process I don't know. Therefore, any subjective intervention means trouble, means that you will force the answer to your way. And I want to make that minimum. So my principle is least interference and maximum smoothness. That's my guiding principle. Least interference is very important. The maximum interference you can have is to give them a functional form. So say, okay, go this, like regression, linear regression. That's it. Okay, you don't care about the data. I have a cloud of data. You draw a straight line through it. Yeah, that's. You think, well, that's simplest. Yeah, but that's the maximum interference, because you ignore every point. You just say, well, this point, this line is a straight line. Unfortunately, in research, you find that kind of curve. A lot of time you see a cloud of data, you draw a straight line through it. They call that the mean or the trend or the whatever. When we come to talk about the trend, we'll come back to revisit that. I think that's the most interference, because you a priori determine the functional form and give only limited freedom for the curve to behave. Yeah. So my guiding principle is least interference and maximum smoothness, and that's why I select EMD. The different spline should not change the scale of IMF, but it may change the energy level, except the B-spline. I'm not sure. I'm not guarantee the B-spline will not change, because B-spline doesn't touch my point. Okay, if it does not touch my point, by the diminishing of variation, it may miss a couple of the extremas, the zero crossings. Yeah. So when you use B-spline, you typically will get a totally different IMF components. Yeah. And the number of extremas and number of maximums are also could also be different. Now, here I change a few words. You have. I think at the beginning I used to all. Here I changed one word to specific. That's important. So EMD is unique with respect to the specific parameters selected. With so many splines, so many different stoppage criteria and all that, how can you talk about uniqueness? And at the beginning I told you EMD actually can generate infinite many decompositions. What do you mean by uniqueness? Uniqueness is the specific uniqueness to specific parameters selected. The parameters you select, the parameters including what? What kind of spline you use? Cubic or Hermit or whatever spline. And once you select that, what stoppage criteria you use? Yeah. All of this determine your decomposition. So EMD is not a specific algorithm. It generates a new approach to decomposition. And within this new approach to decomposition, we may have very different decomposition. Just like EMD in a way it's equivalent to wavelet. And you may have all kinds of wavelet. Each wavelet, base wavelet, is a specific parameters that you select. Okay. And if you selected in wavelet, you select wise, that's fine. If you selected unwise, it may not fit your curve. EMD is the same. So at the beginning, I said, I decide not to select the cubic spline. Too bad. You may have a problem of not even converging. Like at the beginning that I went through the second power all the way to the seventh power. And I find that when I start the fifth power, I already ran into difficulty of simple convergence. Sometimes convergence, but not all the time. Sometimes it does not. So empirical mode decomposition is only unique to the specific parameters. We, in most of the example, or most of the time that I solve problem, I made a very careful notes of what kind of parameters I select. I usually do not say which spline I use. Natural spline is implied. I always use natural spline. If I use any other spline, if you use any other spline, you should mark it. So that now I use, for example, Hermit spline to make the spline less, to eliminate the overshooting to a certain degree. So this is the summary of the spline that I give you. And you'll see that the different spline is different. But most of the time, based on my experience, I found the cubic spline works the best. Yeah, I've been. Many people ask me these questions: why you use a specific spline? Yeah, this is all by experience and by personal preference. But my guiding principle is this: least interference and maximum smoothness. Okay? All right. So that would be all for this hour. We'll stop here, and I will have questions from you. And any questions? No? There's people from the telesite. Can you hear us?
Yes, I can hear.
Oh, you can hear. You have any questions?
Today, so from the Tokyo Tech, someone, do you have any questions? Nothing?
No. Okay. Thank you very much.
Yeah, thank you very much.
Thank you.
Thank you.
All right. Yeah, one question here. Okay.
Can I share my experience of using this spline? Share my own experience.
Oh, your own experience. Sure.
Because it is used for a mobile road.
Building
a mobile road. So it's the curving is for a automobile road. So this control point maybe someplace building you have to avoid avoid a car accident. So you have to make a lot of control point and a curve like this for a car passing through. Very smooth.
I see.
So this kind of spline is used for road design.
Oh, okay. All right. Sure. Mr. Su just told us that the B-spline is very nice to design highway. In other words, if you have a couple of buildings, you don't want the highway pass through the building, you can winding around. I think that's very useful, especially in Taiwan. There are lots of buildings, and you find the road winding around a lot of times. So I don't have experience in that. I only want my curve to pass through my point. That's why I don't find B-spline especially appealing to me. Yeah. Okay. That's a special application. Sure. It must be very useful. Otherwise, all this computer-aided design people will not use it. Yeah. Okay. Any more questions? No more? No more? Let me go off. Easy. All right. Thank you very much.